Good afternoon. Welcome to UniCourse. Welcome to the live Zoom. Today we're looking at Unit 20, Digital Principles, and we're looking at Assignment 4, including hints and tips. This is the final unit for this Unit 20. You can preview, look at all the units in your own time because they will all be recorded. So let's look at Unit 20. Let's look at the Assignment 4. Let's look at the holistically what the assignment's about, and then let's drill down and look at individual areas within this assignment. We're going to analyze the principles of a range of subsystems. We're going to look at how they work in larger systems, and we're going to critically evaluate them for the final part of this assignment. So the first criteria, we'll look at a range of different subsystems. You're going to research evidence to look at various subsystems, which will be including adders and multiplexers and shift registers. We'll then look at the larger systems, how they would work and how they would work within the subsystems. And then for the D4, evaluate a range of different large subsystems with other techniques. Now, as we go through all this, we're going to be breaking it all down. And then as we move closer to the final part of this session, I'll give you an idea how it will be all put together. So let's start off. We're going to look at one subsystem known as a half adder circuit. Now, within the logic family, the half adder and the full adder circuits have been used for many years. Originally, when we first started in the domestic use, they were used in calculators, as we were said, to add up numbers. The actual calculators that you use are a lot more complicated, a lot more complex, but we'll look at a very simple circuit and to see how they work. Now here, to our right, we have this half adder. We have an exclusive OR, we have a NAND gate. And basically what we do is we're going to add 2 bits. And 2 bits would either be a 1 or a 0. So when we add up, we can then have the sum and the carry. And then we have this truth table to our right. We call this one here the half adder. The binary arithmetic is carried out by combination logic. So combination, the way the format is here, by connecting up either the 1 or the 0 or 2 ones. So it is one of the simplest circuits we're going to use, and we use the exclusive OR, and that produces either logic 1 when A is 1 and B is 0, or when B is 1 and A is 0. And you can see to our right how it works out. That the sum here, as we add the 2 ones, when you get above 1, it will carry 1. That's why we got the carry over here. And it's a bit like when you do additions, when you're adding up some big numbers. So the AND produces a logic 1, and the carry output both A and B are at 1. Now, I suggest when you are looking at something like this, it's just to look through it, reflect, draw it out, and think about it through, and to get it in your own mind how you see the circuit works, even to a degree by either drawing it out and producing the truth table, or using a simulator to actually try it out. So here we have the truth table to our right, as I've said, and that is the half adder circuit. So we'll go into more detail. It's, as I said, adding 2 1-bit numbers, either a 1 or a 0, or a 1 and a 1, or a 0 and a 1. And it will allow us to carry the several bits and produce some time as we're adding the 2 numbers together, and then we get into the carry column. It's not practical for anything other than 1-bit additions. So what we've got next, the full adder circuit. So let's see, on the right side, you can see the X34. We've got 2 of those. We've got the AND gates, and that is a symbol for it there. And to the bottom of it, we can see the truth table. And it's something I will look into and see how it all comes together. So if we're doing 2 or more bits, this is where we need to use a full adder and where we can't use the half adder. We've got a simplified block diagram, which is here. And as I say, it consists of 2 half adders, and then the sum of the A and the B from the first add to the second one. And this, what we're looking at, is a basic type of the semiconductor electronic adding device. And it probably all started even before we had ICs and had valves, but this is in a simplistic form, and there's a lot of chips you can use to do all this in one chip. So I'll let you have a quick look at this, and you can just review this again in your own time. So let's now look at multiplexers. Now, the word multiplexer means that we're having lots of different signals all coming into one. So let's look at a very simple one. This is using a mechanical version. And you can see what we've got here is we've got the switch going from here, E, F, G, H, and it allows us to swing it around, allowing us to bring in signals into these outputs over here. And so that's a very, very crude mechanical multiplexer. And that's what they did originally. They used to use mechanical switches. And I would guess that in the old days of the post office, as it was known, British Telecom, they would use that when they were switching phone numbers, when numbers came in into the exchange, and that's then distributed all around the country or all around the world. So here we've got a single pole double through to use here to allow us to then switch in the various signals. And it's a rotary selector. Now, the main disadvantage of this is it will be a lot slower. And because it's mechanical, then it's prone to any failure. And they probably have to replace these every few years, especially if they use continuing. So let's move on to a solid state one. Excuse me. We've got here, we've got the AND gates and NOT gates, and what there is a truth table. And this is a very simple combination circuit which we can use to add 1 or more data into it, which gives us an output. So we've got 2 signals in, and that was giving us a 1 signal out, and that is to a multiple of data. So this uses a steady stream of digital information, of logic signals, and this will operate a lot quicker than a mechanical, and the failure rate is a lot less because it's a semiconductor. As long as you've got power to it, it should last many years. So now let's move on to the next one, which is we've got this 4-bit multiplexer where you've got this output over here, and here we had 4 signals coming in, and we can then connect it up to this various NAND gates, and you've got the AND gate outputs there, and that is allowing us to be able to bring in these signals, and then we get an output to the right. And as I said, it can be used such as a radio channel or a telephone. Now, a lot of the multiplexers that are being used around are very complex ones and use a lot of electronic circuitry. I say we only want to really concentrate on the basic one. Now, in your assignment, you will be asked to do a multiplexer, so it's worth reviewing it, having a look at the UC guide notes and various other web-based material and getting an idea on the sort of circuits that you want to use. Now, if you are using a circuit that you have found either from UniCourse or from one from a web base, don't forget to sketch the circuit out, annotate it, explain it, and of course reference it as well. I will go into more detail about this later on in this video. And finally, about these multiplexes, data is transferred over a long distance, such as transferring data within computers. So they will have very, very complex, very, very fast multiplexes to allow data to be streamed very quickly. Now, we've touched on shift registers last week, but we'll just revise it again. As I say, part of this assignment will require you to investigate, research different types of shift registers. Here we have a very simple one here. It's a parallel shift register. And this is also like a very simple memory. And it's also, we can store individual bits of a binary word, which you can see Q0 and up to Q3, which is only a 4-bit, because you've only got 4 inputs there, which gives you the 4 outputs, which will clock through here using this DK flip-flop. And these are the D-type flip-flops, and they have a sharing common clock. As you can see here, there's clock through here where it says CK for each one of these, and these are the data lines that feed in as well. Providing a synchronous operation. So it's all because you've got the clock. If you don't have the clock, you won't be able to synchronize it properly. So let's look at again. This is a parallel in, parallel out register. You can choose different ones depending how you feel comfortable are. So what you'll do is you'll research different types, and you need to also include, which I've not put on this slide, but the timing diagrams as well. So this one is known as parallel in, parallel out register. So it comes in the address here with D0 to D3, and then you've got Q0 to Q3, and these Qs could be indicators like LEDs. So shift register is to be able to add abilities to shift the stored binary word from left or right. And it can be used for many applications. Now, here we've got one here. As I say, it's quite a complicated one. I won't expect you to produce one like this within your assignment, but it's a 4-bit reversible counter. And we've got common things about it. We can see we've got a load of NOT gates. You've got the AND gates here. We've got not AND gates, but NAND gates. And we've got a series of JK flip-flops. And circuits like this can be created using an electronic circuit simulator. What you can also then do is connect the outputs to some form of a graph generator to look at the timings of it as well. We've got your clock here, which is on the left-hand side. That clocks it all in here to the clocks. And these here, the various inputs come into it. So we're saying it's a 4-bit reversible counter. It's serial in left, you've got serial out. But I wouldn't expect you to do something like this for your assignment. Now, a section which I want to introduce you to is what we call subsystems. Inside microcomputers, inside all types of microelectronics, even control electronics, PLCs, all types of electronic systems, alarm systems, boiler systems, you name it. There will be individual circuits, individual circuit boards, individual systems, and these are known as subsystems. So let us go into it and let's explain subsystems in a bit more detail. So it's a device which will allow us to process electrical signals. So let's look at a block diagram of a subsystem. We first know that we've got non-electrical input signals are converted into electrical form, and here we have it here. So we've got the input here, input sensor, signal processing, and output. device. Each one of these are subsystems. Now, they all can be part of one large system, which could be called, for example, some form of thermometer, a temperature device to control the boiler, or something else. It may be a temperature sensor. So when you got the input there that checks the temperature, then it decides, is the temperature too high or too low? And then it decides, is it going to switch the pumps on or not switch them on? And it's a digital diagram. In this case, it doesn't have to be digital, it can be analog, but in this case, we can say it's digital. And each one of these represent a subsystem. Now, let's look at it in a more digital way. We've got a CD-ROM, a keyboard, mouse, processor, printer, VDU. And each one of these is a subsystem. And inside each one of these, there could be another subsystem to break it even down even further. But we'll just say this, as I say, are all subsystems in one main system. Now, we can also take this further and let's look at it within logic diagrams. So here we have to our left various systems, and we've also got what is known as the logic diagram here, but we have subsystems here. So we've got a multiplexer to the right. We've got a series of gates here, which are part of the inputs here. Input drivers, there's an adder there. And this is another device here, which could be like a counter device. And they're all part of the system. And then the output is over here. So this is part of one big system, but all these are subsystems. Now here we've got another one where we don't actually see the discrete logic side of it. We've just got the ALU, arithmetic unit, we've got the logic unit, and we've got a multiplexer here on the outputs. But these are all part of a main system, but all these are part of a subsystem, each one of these. So this is what I wanted to do, is to introduce you to what subsystems are, which hopefully will give you an idea of the ways that you're looking at completing a question of this in the assignment. And again, we've got one more here finally. So we've got the multiplex here to the right. We've got a full adder here, and these array of logics here on their own as well. And you can determine what they are. And these are probably, you can say really, there is 3 subsystems all built inside this main system. Now, each of these systems can be connected together, and we could also say that we've got these subsystems, as we've seen the other one, and this one here is probably a more complex one, where the subsystems are then connected up. Now, what's interesting is that these subsystems connected up don't have to be discrete components, in other words, separate ones. They can be in one logic chip on its own, and this logic chip could be programmed. And that could be a program which is permanently, or it can be one of these where you can then pre or re-record the program, like the EEPROMs or the read stuff like that. So it depends on what you want to use it for. So there is various chips which you can then put your own signature, make your own, decide what you need that to do with the characteristics it's got or what it's got regarding the blocks inside it. So each one of these are subsystems, but they're all part of one big system, and these could also be programmed. Now this is ALU, arithmetic logic unit. It's a block diagram. As I say, these are all interconnected, and I say it could be one big chip, which you can then program. And now it's both small and large scale integration used. They're all connected directly, and these to make very complex circuits and be able for design engineers to put them into control systems and make the things a lot more simpler. Because if you had to build these individually into discrete components, it would make the circuitry very, very complex. And of course, that it includes combination and sequential circuits within all this. But all of the circuitry is all digital. And then it's for you to work out the flow of traffic, the way the data will then flow through this, and from what you will get as the output. And of course, that the ALU can perform various different operations depending what the program is set out to do. Now here we've got one here which has been simulated. Now I don't expect you in part of the assignment to produce this. Now this one is one from a website that I took a screenshot from, and I say that it's a simulator. There is some software which I'm looking into at the moment, which you can contact me about and I can let you know. But at the moment, we'll just give you as a screenshot. But this is just an example where subsystems are all interconnected here on this system here. And we've got everything from the main adder. I can see it's a counter. We can see these 7-segment displays here in the red. So these will count up to 99, 99, 99. And these are driven by these various shift registers over here. I'm going to quick look at these. And we've got multiplexers here at the bottom here, and we've got other inputs as well, which connect up. Okay, so we've reached halfway of this unit, and we've covered the adders, we've covered multiplexers and shift registers, which are all part of this assignment. But what is important is how you put the assignment together, make sure it's documented, and including all the diagrams and the evidence as well. So let's have a look at it and what we need to do. So we're going to break this down. Describe and present the principal operation of the following 3 logic systems. Okay, now when we do that is we have to look at adders, multiplexers and shift registers. Now one question we ask is, do you need to actually simulate it on either MicroCap or another package like Circuit Lab or other one, Circuit Wizard or Multisim Workbench? The answer to that is that it would enhance the assignment evidence, but you don't have to, as long as you've actually produced a sketch of it, a diagram of it. And what you've done is you've included a typed up explanation, and you've annotated the actual circuit, the logic circuit itself. And that should be okay as regarding doing that one. Now, when we're looking at subsystems, as I've mentioned earlier on, what we need to be looking at is looking at your task 1, and you're looking at adders and looking at multiplexers and shift registers. How are those implemented? How are those fit? How do they work in a bigger system? Now, I've shown you 1 or 2 examples in previous slides, and hopefully you can be able to work it out. Once you've done that, you need to document it. You need to produce diagrams showing it and written explanations. And the diagrams, of course, have to be annotated. Now, you look at each subsystem and you need to show the workings of each one. Now, if you look at a multiplexer and a shift register in one system, it will work, it will do the job for what it has to, but used in another system, it could be used in a different way. The principles of it will remain the same, but the way it's connected or interconnected may give different results. So now, when we're looking at the 3 subsystems, you then have to implement it into a program logic chip. So in other words, that you can purchase the various things, the adders and multiplexers and shift registers in one IC, one chip, and that can be programmed. So part of the assignment is to research it. Now, the first protocol is I would look at the electronic distributors, or you can just plainly Google those three and see what it comes up with. Once you can find that, you need to get some data about it and what you need as the programming side to program that actual chip. So setting out the assignment. So looking at each of the questions, I would recommend is you draft out each of your answers. So you need to research the various digital circuits. You can use UniCourse study guides and further reading, all about circuits, quite a few very, very good websites. But the first port and call is use the UniCourse study guides. Make sure the diagrams are well annotated and include an explanation on how the circuit works. I just don't want to see a screenshot or a sketch drawing of a logic circuit of a subsystem and there's no annotations, no explanations, because that could put you in a that assignment may have to be resubmitted. What's important is include timing diagrams where you can. You may not have to do it, doesn't say it, but if you can include a timing diagram, then yes, please do. It just will enhance overall the documentation. Of course, when you get this information, besides the ones you get from UniCourse, you need to make sure that you've used hard referencing and include the citations on each section that you find information, and also a list right at the end of the bibliography. Now, when you're producing the logic circuits, as you can see the screenshot here, this is a Circuit Wizard one. I've annotated it. I've got the logic analyzer here. I've got the flip-flops here on these counts, the LEDs, and the timer diagram. So don't forget to do that. If you are sketching stuff, and if it says in the assignment here, when you describe the follow operations, I would put screenshots in and also put in handwritten drawings as well to make it more of your authentically your own work. So that is very important. Okay, that is the end of this session. This is the fourth one. You can look at individual ones in your own time, and we'll leave it there. Now, if anybody's got any